Hello everyone, this is Bert de Vries. This is the Bayesian Machine Learning and Information Processing class. Today we're going to be talking about the Gaussian distribution. Up to this point, we've discussed Bayesian machine learning and probability theory, and our formulas had factors like P of x given y and P of x, y, z, and so forth. But we haven't chosen concrete distributions yet. And today we'll do that. We're going to choose the Gaussian distribution, which is for continuously valued data, by far the most common and often used distribution. So what we'll discuss is why the Gaussian distribution is such a popular distribution. There's actually very good reasons for it. And secondly, we'll go over some typical Bayesian calculations with the Gaussian distribution. We'll do Bayesian inference with the Gaussian distribution. So, as before, this video lecture is not a comprehensive overview of the lecture notes. I'd still like you to read through the entire lecture notes, study them. Maybe this video lecture may help in that process, give you some pointers. I'll go over some sticky issues or issues that I think deserve some extra attention, but you still should read the entire lecture notes. So the Gaussian distribution, as you probably know, is expressed by this formula here. It's a probability distribution over x. X here is a random variable, or it could be a vector. And there are two parameters, mu, which would be a vector of the same size, which is also called the mean. And this parameter, sigma, which is called the covariance or the variance, which is for if x indeed is a vector, it is a symmetric matrix. And on the right hand side you see the formula for this Gaussian. It has the typical bell curve, as you know, and so there is a determinant involved and an inverse for the covariance matrix. Also note that it is symmetrical in x, the prime argument of the distribution, and mu, the mean, the parameter. You can exchange them and you have exactly the same function. Now, what not everybody may know is that there is another parameterization of the same function, also of the Gaussian distribution. This, if we write it in this way, this is also called the moment parameterization, because mu and sigma are the first and second central moments of the distribution. But there is another, you can write the same function with a different kind of parameterization. Goes by different names. It's called the canonical parameterization, or the natural or information parameterization. It's also a function of x, of course. Now it has different parameters, eta and lambda. Usually, not in every book, but I write it as n subscript c to indicate that these parameters, eta and lambda, are not the same parameters as mu and sigma. And it has a different function here. Whereas here, for instance, we see sigma to the power minus 1, the inverse sigma. Of course, in this expression, we get lambda, and lambda is exactly the inverse of the covariance matrix, and it's also called the precision matrix. There's another parameter, eta, and there's a relationship between eta and mu and sigma. Namely, eta is the precision weighted mean. So I could have written eta equals lambda times mu, but we can also write it in this way. So eta and lambda can be produced if I have mu and sigma, or the other way around. If I have eta and lambda, I can produce mu and sigma. There are different parameterizations of exactly the same function. Sometimes it's useful to work with eta and lambda. Sometimes it's more convenient to work with mu and sigma. Now, a very important problem is why actually should we use or do we use the Gaussian so much in all basically in scientific modeling? The first answer that most students would give me, and that I would also think of as the most obvious answer, is, well, it's easy to calculate with the Gaussian, right? There's a relationship between the Gaussian and mean squared error, and things tend to actually come out well analytically. This is indeed one of the reasons, but there are also some other reasons, and they are very well summarized in the probability theory book by Edwin James, page 2020. You can actually click on this link and then you'll go to that page in the book. I'll do that now, and then you'll get to page 2020 in James's book, and here you see actually the arguments that I'm going to go through. But James has a whole chapter leading up to those arguments, and that's a very interesting discussion if you want to learn more about it. One important reason why we use the Gaussian is because operations on probability distributions tend to lead to Gaussian distributions. For instance, if I have any smooth function with a single rounded maximum, if raised to higher and higher powers, it goes into a Gaussian function. Now, this is actually very important, because if I do sequential processing, if I process a time series, we do signal processing. I start with a prior, I multiply with a likelihood, and I get a posterior, let's say for parameters. Then if I get new data, I can use that posterior as a new prior, multiply with a likelihood, get a new posterior, which I will use as my new prior for future data, and so forth. So I'm going to get a prior, my posterior for the parameters will now be a prior times a likelihood to a very high power. So there are very good reasons to choose a Gaussian likelihood function, because if I take any smooth function to the high power, it would turn into a Gaussian function. So why not start with a Gaussian function from the beginning? The other reason is, and this is quite a deep reason, that among all distributions with the same variance, the Gaussian distribution has the highest entropy. And we haven't discussed this idea of entropy yet. I hope you've had that in an information theory class. But we'll discuss it later in the class. But for now, just think of it as a generalized measure of uncertainty. And that means that if I want to come up with a distribution for a given variance and make no extra assumptions or minimal extra assumptions, then I have to choose the Gaussian. Right? Because the Gaussian has the highest entropy, has the most uncertainty given a certain variance. And that means that when we choose priors, we often don't want to make a lot of extra assumptions under the hood. So there are very good reasons to choose Gaussians as our priors. There are good reasons to choose likelihoods that are Gaussians. So there are good reasons to do Bayesian inference with Gaussians, getting Gaussian priors, Gaussian likelihoods, Gaussian posteriors, as we will see, and so forth. So that's a very good reason. Now, the second reason is that once we have a Gaussian, then this form tends to be preserved once we do operations on these variables that have Gaussian distributions. For instance, if we add two variables that both have a Gaussian distribution, then the summation z equals x plus y, and both x and y have a Gaussian distribution, then z is also Gaussian distributed. And that's because the convolution of two Gaussian functions is not a Gaussian function. When we do Bayesian inference, we're going to have to multiply a prior times a likelihood if we choose them both to be Gaussian functions, then it turns out the posterior is also a Gaussian because, well, the product of two Gaussian functions is another Gaussian function. And there's more of this stuff. The Fourier transform of a Gaussian function is another Gaussian function. So on the one hand, if I have a set of variables, almost no matter what the distribution is, if I do a lot of operations on them, they tend to go to Gaussians. The central limit theorem is an example of that. On the other hand, once I have Gaussians and I do more operations like add variables or do Bayesian inference, it also stays Gaussian. So there are, aside from the fact that it's very nice to do calculations with Gaussians, there are also some other good reasons, some information theoretical reasons why the Gaussian is actually a very good choice when we do scientific modeling.